So, I think we can start. Let me introduce the next speaker of the afternoon session, Lenka Zalabová, and he will continue our discussion on BGGs, this time joined with Jan Gregorovich. Please, the floor is yours.
Okay, so thank you. I would like to tell you something about BGG operators on homogeneous conformal geometries and conformal circles. So it's joint work with Jan Gregorovich, and I tried not to be technical in the slides, but there is some computation behind. So if you are interested in details, we realized this computation in Maple, and we can show you these computations. But there are no details in the slides, I hope. So I start by a definition of a conformal circle. So if we have a conformal manifold, M with a class of conformal metrics, so each such manifold has a distinguished family of curves that are called conformal circles on conformal geodesics or generalized geodesics. And the most usual definition of a conformal circle is that they are solution of this equation. So here G is a metric in the conformal class. Nabla is a Levi-Civita connection of this metric, and then along the curve we can compute a unique length vector field, which is naturally called velocity, and of course acceleration. And first observation about this equation is that it's nesty. It's pretty difficult to solve the equation directly, so people are trying to find different methods how to describe conformal circles. So our question is how to describe conformal circles explicitly. And what I want to do is I want to use tractor calculus or tractor language. So I introduce some notation. So my notation is that I will denote by T this R P plus 1 Q plus 1, which reflects the metric. And then I will have a standard tractor bundle T that corresponds to the standard representation of SO P plus 1 Q plus 1 to GLT. And analogously for any tractor bundle corresponds to a representation rho of SO P plus 1 Q plus 1 GLV. I don't need any special details on notation, but I should point out that in my language, this COPQ module of the lowest weight is what corresponds to projective slot. Clearly, I have a tractor metric G that corresponds to standard metric on T, and tractor connection, which is just a linear connection on T preserving G. More generally, I have such a canonical tractor connection on arbitrary V. So the first observation about curves is then we can lift each smooth regular curve of non-zero length to the standard tractor bundle. And it is usually done by this. This is some sort of summary of observation, or at least I know this observation by Shilhan and Žádník, but they are much older, I would say. So what we can do is for each curve we define U in this way. Like this gamma is a curve, this gamma bar is just a derivative in the direction. So this reflects the size, so I assume a positive length curve, so this is correctly defined, and I consider this tractor X. And having this, I can consider a series of standard tractors of this form. So simply U is really the tractor, how to call it, tractor velocity, tractor acceleration, and so on. In this way, we can define the sequences of tractors. And what can be proved is that the curve is a conformal circle if the bundle spanned by these three tractors, the first three in the sequence, is parallel for tractor connection, which is basically the same as we consider this U with two bars. The fourth one, it belongs to the span, first three. So having this, we can define this tractor. It's a canonical tree tractor that belongs to the third wedge of standard tractor bundle, and with this we can equivalently say that the curve is a conformal circle if the wedge of this sigma with the u with 2 bars vanishes. So this fact implies that there is a parameterization of the curve such that the conformal circle is satisfied. So this is pretty natural object to study, or a condition to study, and we follow the work of Gower, Snell, and Tagavi-Chabert, and a bit more general, but we reformulate it in a more practical language. So the first observation is that for a representation rho of SO to GLV defining a tractor bundle, we can consider this element, it's a tensor kth power of sigma times S for a section which is parallel with respect to tractor connection. And if we suppose that the bundle where this element lives, which is third wedge power of T, and kth power of this times V contains a trivial SOP plus 1 Q plus 1 bundle, then the projection to this module provides a conserved quantity along the conformal circle. So the idea is to describe conformal circles. We focus on conserved quantities described on tractorial level. And as usual, we start with the simplest examples and we focus on homogeneous conformal geometries. So we consider a conformal homogeneous space, K mod H, where K is the Lie group of algebra of conformal killing fields and H in K is a stabilizer at the origin. Then it can be proved that there is a linear map, usually denoted by alpha, going from K to SO such that this condition is satisfied where Y1 is from K, YH is from H, and here we just compute the two brackets as follows. Firstly, we map the two vectors and make a bracket in SO, where here we compute the bracket in K and then map. And this difference vanishes. And the second very natural condition is that this K mod H is the same as SO mod P via alpha, where P here is the algebra of Poincare conformal group. And for those who know from the language of paraboloid, the geometries and extension, this is what remains to infinitesimal level from what people in parabolic geometries calls an extension functor. And it's enough for us. We call it a conformal extension, and of course there can be many extensions, and what we do is we work with alpha determined by a normalization condition, which is some more restriction with, naively said, gives us the most beautiful extension to work with. So having this, there is the following thing. For a representation rho, defining the tractor bundle V, there is a bijective correspondence between parallel sections of tractor connections and elements of a maximal invariant subspace of V with respect to the action of rho alpha, or the image, K image of rho alpha, such that if we this rho alpha restrict, it is a representation of this subspace. So basically the next step is if we can describe this subbundle somehow. And we can, but anytime you need to describe something explicitly, you need some reasonable coordinates. So I try to introduce our coordinates we use to description. So we consider exponential coordinates, which is a map from C to K mod H for a reasonable complement of C of H in K, and of course the lift of such complement is available. I don't want to go here into details. I know that there are many various types of exponential coordinates. People call it coordinates of first type, second type, depending on the K and Iwasawa decomposition of all the algebras in the game. But what we do is we simply always take the most convenient ones for doing computations. But they are always exponential. It belongs to this exponential world. So what we do, I was trying to picture here some diagram to find it easy. So we have our homogeneous space, K2, K mod H, and here from this complement C we have coordinate, this coordinate map C, and it's left, so we can go to the tangent level. So we have a map from TC to K, and of course composing with Maurer-Cartan form of the group K, we get a map that I call nu. It's a map from TC to K, and having fixed this map, I can describe in coordinates all other objects. So I'd like to describe the tractorial object in these coordinates. So firstly, I can define alpha minus 1 nu. This composition, it simply is that I go here, and here, and this minus 1 should know that this SO is basically graded as G minus 1, G0, G1, and restricting to here, we get a map from TC to RP plus Q, which is the coframe we do all the computation. We can describe as well the tractor connection in these coordinates. So the tractor connection has this simple form. This del stands for the fundamental derivative part along C, and this rho alpha nu is the algebraic part. Again, the tractor bundle trivializes then in this form, so each bundle can be viewed as C times V. Parallel sections are functions from C to V such that they are parallel. And if we really want to describe it in coordinates locally, then we do it in this way. We consider the parallel section at origin and use this exp on minus rho alpha x for each x from C. And this really, it's not like this. This just suggests that we use our exponential coordinates, so according how we really like to split A. So how to find this SO? So we can find it inductively by the following procedure. In the first step, we introduce a set as 0, which is a set of all V such that the row K acts trivially for all x0, x1 from K. Here this kappa, sorry, here this not K but kappa. Here kappa is basically this term, and it is a curvature of the extension, just curvature of the geometry at one point. And then going inductively, we apply this rho alpha again and again. And since V is finite dimensional, it stops for K large enough. And by definition of the S0 of the beginning representation, we get that rho alpha is precisely restricts to a representation. The representation, this rho alpha is a representation from K to GLV, and it restricts to the representation from K to GLS. And this S is precisely the maximal subrepresentation you're speaking here. So the main thing, or main observation, we can compute this explicitly. So back to tractors, we can describe also these three tractors in coordinates. So consider this X, U, and A. Tractors are viewed as curves from R to T. This X is my X, and U and A can be written explicitly in this form using the fact that I already know how the tractor connection looks like. And using this, I can write the tree tractor in this way, and the condition characterizing the conformal circles takes this form. It's enough simply to view behind this explicit description of the tractor connection. So we can describe also this explicitly. And now, what to do? Parallel sections correspond to normal solutions of BGG operators. It's somehow known for the tractor connection. But normal solutions are rare, and general solutions need not to give conserved quantities. But there is an observation of Gover, Snell, Tagavi, Schaber, which is pretty general, but not that possible to use it directly. But if we reformulate it for homogeneous geometries described in our C coordinates, we can easily say that if S from C to third power of T be a function corresponding to some Kilikiano 2 form, then this quantity, which is a tractor metric applied on the 3 tractor and S, is constant along a conformal circle. So this corresponding to really means a splitting operator or something what we can find explicitly in homogeneous setting. So our goal basically is that we would like to find all solutions, which means that we want to find a prolongation connection. And this is the most technical part of the slides, just for those who are interested in details, how to find a prolongation connection. We shall modify this composition row alpha by an H equivariant map from K to GLV, vanishing on H, and we do it inductively as follows. So we start with 0, and in each induction step, for certain integer, we just compute this expression. We naively set each such component, erase each such term, erase a component in the proper homogeneity. And what we do is that this never does lower the homogeneity, and there is only finite number of irreducible grading components. So it stops, and when it stops, we have the psi that gives us the prolongation connection. So then, finding all solution is very analogous to finding all parallel sections or normal solutions. So we repeat the same procedure, but for prolongation connection, not the original one. So again, the procedure stops, we find S with the same properties, the description in coordinates is the same, and so on. So what we can do is we compute solution space explicitly and recognize normal solutions. So now this was some sort of how to do something, and now how to really use it to deal with examples. So I have here 2 examples, and the first example is a Heisenberg group. So 3-dimensional Heisenberg group. Let us consider the group K, or K mod H is this group. Our C is the whole K for its Lie group, so simple homogeneous space. Algebra of strictly lower triangular matrices, and we consider this coframe, which is pretty natural coframe. This is a contact form. And this gives us a metric of signature 1, 2, which gives a conformal class of K of this form. So now if we consider a curve parameterized by arc length, it looks somehow like this in this C coordinates. Then the first 3 tractors take this form. Here is 1, 0 because of the arc length parameterization, U and A. And considering these condition explicitly gives this set of these 3 equations, and the 4th one is for coming from this orthogonality of U and A. So if we have this, we can use it for further computation. And I just give here the results. What we find out is the following quantities are constant along conformal circles. And if you want to see behind the Kilikiano 2 form, so the space S of our solutions in the standard basis, which is lexicographically ordered, takes this form that all solutions are non-normal, and this is for me the projective slope. One can deal a bit more with this to get some more explicit description of the curves, but it involves pretty nasty integrations anyhow. So I don't think that I want to give here details. So this is maybe more interesting example, split version of Bini study metric. So let us start with the unique invariant split signature metric on this symmetric space, SL n plus 1 over GLN. And firstly, let us start with n equals to 2 to show you the incoming data. So we consider this exponential coordinates. So here is this, the wall, you know, this is this SL3, and if you factorize over GLN, this is precisely what remains here, and we decompose this very naturally like this and like this. Then we consider this coframe, and the metric of signature 2 giving us the conformal class looks like this. So in these exponential coordinates, we consider this curve. Then we can describe all the three tractors like this. And for those who are interested in details, here is how the solution of corresponding BGG looks like. This could be generalized or viewed in general dimension. So putting all these things together gives us the following result. So the following curves are conformal circles for all C, or for real C bigger than 0, in our exponential coordinates, and their K orbit has codimension 1. So I don't think I need to read it, everyone can read. I'd rather stop here.
Much, Lenka. Any questions, comments? Yes.
Have you ever thought about lifting the curve into the adjoint tractor bundle instead of the standard tractor bundle?
Yes, but it wasn't nicer.
Or was it worse, or was it as nice?
I don't remember really, but we somehow decided not to proceed.
No, because the reason is this is what you do here is very specifically conformal. Whereas if you try to go into adjoint tractors, it may be more general. Usually there are no restrictions on the geometry.
That's true. Yes, we can try again.
Further questions, comments? Not the case, so let me thank Lenka again.